So now it's time to apply what we've learned up until this point about sampling distributions of the mean and what we've learned about describing the sampling distribution of the mean. So now we're going to kind of put it all together into different application questions. So in this lecture, we will cover example 10. So this is section 8.5, calculating probabilities using the sampling distribution of the mean. So let's read this. So it says, last year, the mean batting average of all Major League Baseball players was .275 with a standard deviation of .018. Assume that batting average is normally distributed. A, what is the probability that a baseball player selected at random has a batting average of .248 or less? So this actually looks very familiar to what we were doing in chapter 7, doesn't it? And remember what I was saying to you guys, whenever we read a word problem like this and then it's going to ask us for a probability, forget about the question for a minute, right? Just let's extract and identify all the important pieces of information because it's going to make it that much easier for us to complete the problem. So who's your population of interest? In this case, it's all Major League Baseball players. What's the variable of interest? In other words, what are we measuring or studying about them? It's their batting average, right? So in this case, X represents their batting average, and I'll use BA for short, batting average. We also know the mean batting average. So the mean batting average for all these players is .275. And we're also told that the standard deviation is .018. So we know that mu is equal to .275 because that's the mean batting average for all the baseball players. And then sigma, the population standard deviation, is equal to .018. And then we're also told one last really important piece of information, that batting average is normally distributed. So we know that X is normal. Now let's go to the questions. So part A says, what is the probability that a baseball player selected at random has a batting average of .248 or less? So remember what we were doing last chapter. We were rewriting the words, right, in English into mathematical notation. So we want to find the probability that, right, that's how we write that using probability notation. If we were to take a baseball player at random, that his batting average, and batting average is just X, right? So his batting average would be .248 or less. So less than or equal to .248. So we would have to use that inequality, right? Less than or equal to. So that's what we're trying to solve in part A. Well, how do we do that? Well, we're looking for a probability, and we know that X is normally distributed. And remember what I stressed in chapter 7, area under the normal curve is equal to probability, right? So if we could locate this area, this proportion of area under the normal curve, we could use a normal table or just use the calculator to look up our value, right? That proportion of area. So in A, we want to find the probability that X is less than or equal to .248. And we have a normal distribution, right? So let's sketch our normal distribution. Mu equals .275 goes in the center. And we want to find the proportion of area where X is less than or equal to .248. Now, .248 is less than .275, so I'm going to put it to the left. And we want the area that's less than or equal to. So it's the area to the left. Take a second, think about how you're going to find that area. You're going to use normal CDF in the calculator, right? And we need lower upper mean standard deviation when we're going to use normal CDF. So the lower bound is going to be negative E99, right? We're coming in from the left, so it's going to be negative E99. And then the upper bound is going to be .248. And we have a mean of .275 and a standard deviation of .018. So let's do this together in the calculator. So second and then the VARS key, right? We've done this a bunch of times. Option 2 is normal CDF. We're coming in from negative E99. That's the lower. The upper is 0.248. The mean of the distribution is 0.275. And the standard deviation is 0.018. Then we could paste and enter, and we get about 0.0668. So this area is 0.0668, and that's going to be our answer, right? Because area equals probability, so that's going to be 0.0668. So in other words, if we were to select a baseball player at random from this population, the probability that the batting average of this player being less than or equal to 0.248, the probability is going to be 0.0668. So there's only about a 6.68% chance that if we were to take a batter at random, his batting average would be less than or equal to 0.248. So this was a chapter 7 question, and I snuck it in here, 1, for a review, and 2, because now I want you to see how what we're doing in chapter 8 right now in B and C is going to be different, but it almost looks exactly the same, and I don't want you to make a mistake. So let's look at B. B says, what's the probability that the mean batting average of a random sample of 50 players is at most 0.280? This almost looks very similar to part A, right? But what's the big difference from part A and from every question that we did in chapter 7? I see it right here. We're sampling now. We didn't do that in chapter 7. We were just taking a data value at random and we wanted to know, okay, what's the probability that it's greater than, less than, between? But now look what I'm doing. I'm taking a sample of n equals 50 players, and I want to know what's the probability that the mean batting average is going to, of this sample, is going to be at most 0.280. The key words here are mean batting average of a random sample. The mean of a sample is X bar, right? So what I'm saying is, what's the probability that if I were to take a sample of 50 players, that the mean of that sample, which is X bar, is going to be at most or less than or equal to 0.280? That's what I'm looking for right now. But you see a huge difference from part A and what we did in chapter 7. It's the random variable, right? In chapter 7, X was my random variable. Now in part B, X bar is my random variable, right? I'm asking, what's the probability? So let's do part B over here. What's the probability that X bar is less than or equal to, or at most 0.280? So I can't use this information over here to answer the question, because this information that I just boxed off here in red is describing X, but X is not my random variable. X bar is my random variable. So we have to know about X bar. We need to describe X bar in order to answer this question. But we did that. We just spent the last few lectures describing X bar. So let's describe X bar right now. X bar is going to be normal because we're sampling, we're taking these 50 players from a normal population, right? Because it says batting average is normally distributed. So we're sampling from a normal population. And now we need to know the mean of all the X bars. What's the mean of this distribution? Well, that's equal to mu, which is 0.275. And what's the standard error or the standard deviation of X bar, right? Because we need to describe X bar. What shape does it take? What's the mean of all the X bars? What's the standard deviation? Then I'll be able to answer some probability questions. So sigma sub X bar is equal to sigma divided by the square root of n. So we're going to have 0.018 divided by the square root of 50. Let's go 4 places. So 0.018, that's kind of like a rule of thumb. Anytime we calculate standard error, a lot of times it's going to be a decimal that doesn't end. And we typically go 4 places. So that's going to be about 0.0025. Now I'm ready to answer this question, the probability that X bar is less than or equal to 0.280. I know X bar is normal. So I could sketch a normal distribution. This normal distribution represents X bar. So then that means the mean of all the X bars has to go in the center, mu sub X bar. And we know that's equal to 0.275. Now we want to know what's the probability that X bar is less than or equal to 0.280. Well, where's 0.280 within this distribution, right? It's going to be to the right of 0.275. So let's say this is X bar is equal to 0.280. Just write that X bar a little bit neater. And we want the probability that X bar is less than or equal to 0.280. So I'm going to shade to the left. Okay. So you should be saying to yourself, I know how to do this, right? Because even though this is a different random variable than we're used to, it's not X, it's X bar, but X bar is normal. And we know how to find an area under the normal curve. And remember, area equals probability. So once I have this area, that's going to be my answer to this question. So it doesn't matter if X bar is my random variable, it's normal. We could still use normal CDF, just like we did in chapter 7. So we just have to plug in the parameters into our function in the calculator. So since we're coming in from the left, my lower bound is going to be negative E99. My upper bound is going to be 0.280. My mean is 0.275. And my standard error is 0.0025. So let's go to the calculator, pull up normal CDF. My lower is negative E99, but now my upper is 0.280. The mean is 0.275, and the standard deviation is 0.0025. And we get to 4 places, 0.9772. So this is 0.9772. And that's the answer to my question. So this represents the probability that if we were to select 50 players at random, that the mean batting average for that group would be less than or equal to 0.280. So there's about a 97.72% chance. So it's pretty likely. And now let's go to part C. So part C says, what is the probability that the mean batting average of a random sample of 15 players is greater than 0.250? So I'm going to erase part A. And we'll do part C right here, just to make some room. Okay, so part C we'll do right here. So what is the probability that the mean batting average of a random sample of 15 players is going to be greater than 0.250? Very similar to B, except now I'm changing the sample size. So now we're going to take a sample of n equals 15 players. And I want to know what's the probability that the mean batting average for this sample, so that's X bar again, right? So what's the probability that the mean of the sample is going to be greater than, so I'll use the appropriate inequality, 0.250. So that's what we're solving for. So again, my random variable is x bar, it's not x, and we have to describe x bar. I need to know its shape, mean, standard deviation, and then we could solve the question. So again, x bar is normal since we're sampling from a normal distribution. Mu sub x bar is still equal to mu, which is 0.275. That's not going to change. But think about what changes when sample size changes. What gets affected by sample size? It's the standard error, right? Because we have to divide by the square root of n. So we need to recalculate sigma sub x bar with this new sample size. So we're going to take 0.018 and divide it by the square root of n, which in this case is 15. Now, I want you to see what happens. Think about it. We're making the denominator smaller, right? So the sample size is decreasing. N got smaller. So we're dividing by a smaller number. So what's going to happen to that quotient? What happens when I take a fraction, right? I keep the same numerator, but I divide by a smaller denominator. The number is going to get bigger, right? So I'm expecting that since the sample size went down, the standard error is going to go up. It's going to get higher. So let's divide this out. So let's take 0.018 and divide by the square root of 15. We get 0.0046. Which is bigger than when the sample size was 50, right? When the sample size was 50, my standard error was smaller, it's 0.0025. So I'll make a note of that before we end this lesson on the whiteboard, that as our sample size increases, the standard error gets smaller, but as the sample size gets smaller, the standard error increases. It'll have the opposite effect. So I'll write that down, but let's just finish this question. So now let's get this probability. So I'm going to sketch my normal distribution. Mu sub x bar is going to go in the middle. So mu sub x bar in this case is 0.275. And we want to find the probability that x bar is greater than 0.250. 0.250 is less than 0.275, so I'm going to put it to the left. So let's say here's x bar is equal to 0.250. And we want to find the area greater than. So I'm going to shade the area to the right. And since this is a normal distribution, again, we could use normal CDF. My lower, where the shading begins from the left, is 0.250, and we're shading indefinitely to the right, so the upper is going to be E99. So let's go to the calculator. We're going to use normal CDF. So we said the lower was 0.250. The upper was E99. The mean is 0.275, but now we have to change the standard error, right? It's 0.0046. And now we get about 0.9999999, but if we round that 4 decimal places, it's approximately 1. So the probability, or this area under the curve, is approximately 1. So if we were to take a sample of 15 players and calculate the probability that the mean of the sample, the mean batting average, is going to be greater than 0.25, there's about a 100% chance. So before we wrap up this lecture, and in the next lecture, we'll do a couple more examples. I just want to write down something important on the whiteboard. So as sample size n increases, the standard error of the mean which is sigma sub x bar, it decreases. It gets smaller. So as the sample size increases, the standard error goes down. As sample size n decreases, just like we saw in this last example, the standard error of the mean, sigma sub x bar, increases.